In the previous video, we were looking at logistic regression. We were using a data set about penguins, and we noticed that in the data set there was missing information. So for example, you can see here we imported the data into Python. We can see that for index row 3, there's missing information for bill length, bill depth, body mass, so on for a particular row of data. So we mentioned in the previous video about the missing information and how do you deal with that. So let's take in this short video here, just a quick aside, to talk about missing information. Now, throughout our videos, we have talked about different methods and how they are impacted by missing information. So for example, when we looked at our short-term forecasting methods, like moving average and weighted moving average, it couldn't have missing information. And so there what we did is we filled in the missing information by maintaining the same technique. So we just went further back in time and then used the moving average to find estimates for the missing information, so we could then use the moving average to find future information. So we talked about consistency of assumptions, making sure we maintain that. So that's really important as we think about dealing with missing information is one, can our model handle missing information? And then two, if it can't, the method we choose to deal with the missingness really needs to not have conflicting assumptions within what we're doing. So we can't use kind of two different models that have two different assumptions, or we have to think about as we add in the missing information, or if we put in things into that missing information, how that's going to impact the model and its accuracy. So it's really going to come down to a number of things in terms of choosing our approach. First, we need to identify the type of missingness that we have. So the first type of missingness is what is called missing completely at random. This is a cause of missingness that's completely independent of the data. So if I go back to our data set here, we can see that that missingness, so let's say we're missing here this particular penguin's information, if it is not based on any other variable or the variable itself as to why it's missing completely at random. So maybe it started raining when we were collecting this information, and so we spotted the penguin. We know what island we were on, but we don't have any more information beyond that because it rained and the penguins all ran away. Missing at random, right? Has nothing to do with the type of penguin or any of these measurements as to why we don't have that data. The next type is called missing at random. So if we're missing at random, the cause of missingness is related to another variable. So if we're going back to our data set here and we're missing the bill length, if it is just really hard to measure bill length of Adelie penguins, and so the fact that it's an Adelie penguin means that the other variables are more likely to be missing, this is what we call missing at random, okay? Compares this to missing not at random. Missing not at random was where the cause of the missingness is related to the value of the variable that is missing. So this would be the fact that we are less likely to have a bill length measure if it's a longer bill length, okay? So shorter bill lengths we can measure, longer ones we can't. So this missingness is tied directly to the variable itself. This type, this missing not at random, is the biggest problem, okay? Because there's this whole subset of that variable that's not being accounted for. So that one is going to be an experimental design issue, and we need to figure out a way that we can capture the full variability of bill length. Okay, so if we have missing not at random, we need to redesign a research project. Missing at random, it comes down to the fact that what is it our model is trying to do? So the problem we're going to have is that if we're missing information, particularly for Adelie penguins, it's going to be much harder to predict whether or not you have an Adelie penguin. Okay, and so a model to try to predict Adelie penguins is not going to be successful if we have less information about the Adelie penguins versus the Gen 2. Okay. Now, if we're trying to predict Gen 2 penguins, not Adelie, it's going to have some impact, but less, right? So it comes down to what is the model trying to predict. In both cases, though, you really want to create a system, design a research project that minimizes the missing at random and the missing not at random. Okay. Now, missing completely at random, so the cause of missingness is not tied to the variables that we're looking at, is less of an issue. And then the question becomes, how do we deal with it? So missing completely at random, we can do something about. The missing at random, missing not at random really jeopardizes the project. We need to redesign some of the structure. So if we're missing completely at random, what do we do? Well, we talked about how with the moving average, we would forecast those missing ones using that same consistent model to maintain the assumptions. When we were forecasting using a trend longer term, we could just ignore if we were missing data from 2009. We still built a scatter plot. We still did the line of best fit. It didn't matter. We simply ignored it. We're assuming, of course, that it's missing completely at random, that the reason it's missing is not because there's something different in that particular number that it wasn't collected. Okay. Now, we know that's not the case when we look at, for example, population data. If we're trying to forecast the population of a town, well, towns don't do a census if they think the population has fallen, because then they get less funding from provincial, federal governments because they have a lower population number. So they think the population went down, they don't collect the data, which means that information is not missing completely at random. That data is missing not at random. It means that numbers that go down within that variable are not being captured. Right? So when you create that forecasting model, it's making the assumption, as we skip the missing information, that it's missing completely at random, not that it's actually because it's dipping down. So for those models, we could just skip the missing information. And also if we're assuming completely at random. Now, what do you do in other models? Well, as we looked at the logistic regression, if our focus is going to be right on the relationship between those predictor or independent variables and the variable we're trying to predict, the dependent variable, we need the data. So what do we do? In the video that we just looked at, the logistic regression one, we dropped the missing information. Now, to prevent overculling, so not removing all these rows, what you could do is create a smaller table with just the variables you cared about, and then use that drop NA to get rid of the ones that are missing. And that way, if you were just missing the sex of the penguin, but you had bill length and flipper length, you wouldn't remove one of your rows of data where you had everything you needed. So we would instead just create a table of just the variables we need, and then we would drop the missing ones, the NAs. Okay, so that's one approach. That's what we use in the logistic regression one, right? There are other methods for dealing with missingness. You could, for example, replace the missing information with either the median value for that variable, the mean value of that variable, or a random sample from the rest of that variable numbers, right? The only issue is when you start to do that, then if we are trying to look at statistical significance, the impact that, in this particular case, the bill length has on being an Adelie penguin, if you start to fill these numbers with all of the same number, the same mean, the same median, then the impact that bill length has on being an Adelie penguin is lost because we have less variability in the data. If you randomly pick numbers to go in there, then the impact it has in combination with the other variables that you do have says, okay, well then this bill length is less important, because it's not like when bill length is high, bill depth is low, and when bill length is low, bill depth is high, right? So if you are starting to fill this with randomly generated numbers, then the significance of the variables get lost. So that's why, for the most part, if we are missing completely at random, we mostly just drop as long as our data set is big enough. If our data set is smaller, then we have to start looking at these alternative methods. There are more complicated methods for dealing with missingness. There's the Bayesian approach. So the Bayes methods that we've talked about in some of our other videos says that we have the information from this data set, but we also have prior information from other research, from other data sets, from distributions we've seen of variables. And so we're using that to inform, helping to narrow down what this missing variable or data might be. So it's not just that they all get replaced with the same thing, or that we lose the relationship by just randomly pulling a number to put in. Instead, we have a more informed replacement because it's based on the distribution of the variable, additional data from previous research that can better inform whether that number that should be replaced should be higher or should be lower. So those are the more advanced methods for dealing with missingness. We'll add a video in the future on some of those Bayesian methods. But for now, as we look at a lot of these approaches and as we get into things like neural networks, mostly we are assuming missing completely at random and we are dropping, because that then doesn't add any unwanted bias into the models, pushing it one way or the other when it shouldn't be. So in terms of the cleanest, not biasing it at all, is to drop it, but you can only do that if your sample size is sufficiently big.